Well, welcome everybody as you're trickling in from the waiting room. I'll just give a couple of minutes to make sure that everybody's been admitted. Okay, the numbers seem to have steadied off now. So yeah, welcome everybody to today's event being delivered jointly by the Offshore Renewable Energy Catapult, Orca Hub, and the Net Zero Technology Centre. I am Alex Loudon, a Senior Technology Acceleration Manager at ORE Catapult, with a special focus on robotics and autonomous systems. Quite a clunky name, I'm sure you'll agree. So I'm sure robotics and autonomous systems will get shortened to RAS and indeed robotics as we talk today. So I'll say a few words first about why we're running this event while people are tripping into the waiting room still. Our three organizations are all running robotics innovation programs with a growing crossover between technologies developed for oil and gas and other extreme environments, along with offshore wind. And we wanted to end 2021 with a showcase of some of the most exciting technologies to emerge from our programs this year, focusing on how they solve the remaining barriers to robotics deployment at offshore sites. So we'll be ending the day in an hour and a half or so with a Q&A. So please do start getting your questions into the Q&A box. That's the Q&A rather than the chat box. And we'll ask all of our guests who have presented to reconvene at the end to answer them. There are some house rules on the screen at the moment, so please do take a moment just to familiarize yourself with them. But first of all, we'd like to start by introducing what the robotics innovation ecosystem is in the UK, and a few words about the ALTA project that brings our three organizations together. So joining me for this first discussion is Professor Ivan Petiot, Director of Orca Hub, and Sakshi Sarkar, who is a project engineer from the Net Zero Technology Centre, where she works in the area of offshore energy 4.0. So Sakshi and Ivan, welcome to you both.
Welcome, thank you.
So I'd like to just start by outlining the kind of robotics opportunity for the UK, which was mentioned earlier. We published a research paper back in September trying to quantify what the potential market size for RAS in offshore wind and related environments, including onshore wind, oil and gas and nuclear. So viewers, the links to that research paper is in the chat box. So do take a look at the figures at your leisure. But I'm interested to hear from the two of you, Ivan and Sakshi. What's your view on this? Where are we now in terms of RAS innovation in the UK and in terms of the UK's kind of leadership in global markets? And ultimately, where are we trying to be in the future? So Sakshi, can I start with you?
Yeah, thank you, Alex. I think it's a really great question. I think right now in the UK, we are doing really well in the RAS innovation area through, I guess, organizations like ourselves, NZTC, there's ORE, and also the Orca Hub. We are creating that pathway. I know at Net Zero Technology Centre at NZTC, we're investing a lot in RAS developments through the range of TRL levels, all through to like TRL 8, so close to readiness for commercialization. We do have some challenges. We do have some challenges in the industry around adoption and sort of long-term field testing. That's a space that we are currently working on quite actively. In terms of the leadership of the globe in the global market, I think collaboration is key. So, you know, events such as this, the relationships that we have within the three organizations, we're working a lot with developers in the EU as well as the UK. So really it's how we can continue that collaborative work and build upon that. Alter will fill that gap a little bit, so I'll talk about that a bit later as well.
Thanks, actually. And Ivan, where do you see us sitting in the UK and where do you see us going in the future?
So I think to me, it's clear that we've got a long way in the research side, especially through the hubs. So not just the Orca Hub, also the Rain Hub and the other hubs in extreme environments. Well, we've kind of started a journey of showing to the industry what's possible. In the process, we have also engaged with industry a lot more deeply than we used to, I think, in academia. And I've realized that there are areas where we are there. So I would think that remote inspection of offshore assets or extreme environment, even inshore, wind farm, etc., that's something we can now do. And with the advent of 5G and high-speed communication, I see no reason why in the next 5 years, all of the inspection could be automatized by robots. That could be either permanently deployed on the structures, or could be deployed by other autonomous systems like surface boats in the case of offshore wind to do the inspection. What we've also realized is there's a number of SMEs who are really popping out really quite quickly in the UK. And I think the UK at this level of the technology transition and adoption is becoming a world leader. And I think that thanks to the government, thanks to people like you, Ore, and NTZ, that enables this kind of nurturing of companies. Where I think we have a big gap, and that's not something we're going to solve tomorrow, is around manipulation and advanced manipulation. So I think at the moment in robotics, we fall short of being able to solve the whole problem, because we can do the inspection very well. When it comes to maintenance, manipulation, repair, I think we still have some work to do.
That's a really nice kind of summary of, I guess, where robotics is at the moment. So thank you for that. And I suppose as we look into the future, one of the key things that robotics needs to do to take advantage of this huge opportunity that it has is to solve some of these key kind of innovation challenges that exist within our kind of adjacent sectors. And I suppose you've kind of touched on that, Ivan, with indicating that manipulation is maybe one of these key innovation challenges. But what are some of the most imminent challenges over the next couple of years that we need to solve with robotics, or that robotics has an opportunity to solve? Over the next few years, what are those imminent challenges, Ivan?
Okay, so I think inspection is solvable. Some of the manipulation and repair is also solvable. We see solutions appearing which are like a Bladebug, which are really tailored to one problem and do that quite well. I think it's more the generic repair that is a bit further away. Also, I think what we could do is quite quickly adopt remote teleoperation. So we won't do autonomous repair and inspection tomorrow, but we can do autonomous inspection and teleoperated repair, where you remove the people from the platforms. And that I think is something we should focus on initially in the next 2 to 3 years, and then adopt the rest of the more advanced technology, which involves a mixture of AI and robotics further on the line.
And can you just briefly mention what the for the benefit of the people on the webinar today, what the benefit of taking that intermediate step of teleoperation is in terms of kind of cost and risk and things like that?
Well, okay, yeah. So I think first thing is you don't need anybody offshore. So you don't need a crew. So that means your ship can be virtually autonomous. So you don't need a big crew. You don't need to deploy people offshore. You can probably work in a wider variety of weather windows, and you are really also, you can probably bring on the job a lot of people who couldn't be there physically. So you could have people effectively calling in to do a specific, very difficult job or technical job from somewhere in the US if you needed them to be there, but they would virtually be there for the amount of time they need to be there. So I think you improve the skill set potentially of the people doing the job, whilst removing the need for them to be on site. So I think, and also the carbon footprint would be reduced, I believe. But more importantly, I think if we're going to have to large-scale wind farms, like hundreds of wind turbines, we're going to need something that's much more efficient than what we can do now, because it won't be feasible to go inspect and repair all those wind farms with crewed manned ships.
No, thank you for that. And it's actually, you know, the NZTC, I guess, approaches this from a slightly different angle. You straddle both how the oil and gas industry is kind of developing and changing over time, but then how that interacts with other offshore energy sectors, and how we move towards ultimately net zero by 2045 in Scotland. Does that change your view on what challenges are imminently solvable for robotics?
Yeah, I think there's perhaps maybe two sides. So Ivan's touched on one. I think robotics is definitely like a key enabler for getting assets to be, or the energy industry to be at a net zero level or a carbon neutral level. So there is a very key benefit in deploying robotics, is that you're reducing your carbon impact of that operation, of that particular task. Because as having things offshore obviously makes everything inevitably more complicated, logistically, and all sorts of other reasons. I think the other key innovation challenge, so this is maybe coming from a different angle, is that we have an imminent challenge around the enabling technology for deploying robotics. So this is things like comms platforms, or having that low latency, sort of high bandwidth ability to enable remote operations effectively, to have the reliability in remote operations. So I know at NZTC we are looking at how we can deploy 5G comms, for example, and create that mesh network. So I think, yeah, I agree with pretty much everything Ivan said. There's not much more to add to that. I think the other thing that we're also lacking is at the moment is maybe the skill sets, the supporting skill sets for deploying robotics and maintaining the robotics themselves. So we're talking about removing humans from offshore environments and replacing robotics, but they will be upskilled, and there's a need for that as well. And making sure that they are released to do other work to create that efficiency in the organization.
Yeah, no, I think that's a really good point. Those building blocks are crucial, but then also, I guess, making the best possible use of that kind of the human brain, I guess, as we possibly can, and deploying that resource that we have where it's most needed. And so I guess that brings us nicely onto the last talking point of this introductory session. And I want to briefly look at the respective roles of our three organizations and how we fit into this robotics ecosystem that's growing in the UK. So at ORE Catapult, our robotics offering covers support for technology development, testing and demonstration of new robotic systems, as well as their commercialization. And really we focus on how we can de-risk that adoption of new technologies by industry. So giving end users confidence that new technology will perform as required, but also for companies developing new robotic technologies, we're trying to remove any barriers to development for them. So access to representative testing and helping them to validate the market potential of their systems. But I'm interested to hear, I guess, from the horse's mouth, Sakshi and Ivan, can you just give us a few sentences about what Orca and NZTC are doing? So Ivan, I'd like to start with you, if that's okay.
Yeah, no problem. So Orca was set up as an EPSRC project. So it's low TRL 1 to 3, but in practice we went a bit further than that. So went probably all the way to TRL 5 in general. And we see our role as the university, and in the context of, I think, what's happening post-Orca, which is National Robotics, which is a research institute we're creating in Edinburgh at the moment, to actually do the research that needed to bridge the gap between some big end user needs and the time where it's ready to be really tested in a very realistic environment in the ORE Catapult. So our role is to take a problem, design the technology, do the research, and test it in what we call living labs, which are scaled down mock-up models of what the problem is. But we're really interested in working on real problems. So we still do the basic research as part of our remit in the universities. But in Orca and National Robotics, our aim was to really take that basic research and apply it to a problem, which in general will generate new research problems. Some of them will be first fundamental, some of them will be more applied, and then partner with the right people to solve those problems. So our aim is to get all the way probably to TRL5, maybe up to 6 potentially, but really be the place where people can come with a problem in robotics and say, we'd like to use robotics for that. How would you do that? So there's some kind of consultancy. And then define the problem a bit better with them and try to propose solutions and demonstrators that can then be turned into products by SMEs, company, and tested in our catapult. The other thing we see our role is the skills side. So Archie mentioned there's a skills issue. We are tasked and willing to train people. So we have a number of undergraduate programs and postgraduate programs, but I think we're also in the process of developing a CPD program. So we can upskill some of the industry workers so that they can adopt and utilize robotics technology looking forward.
Thanks, Ivan. That's useful to see where you sit in that broader ecosystem. That's really helpful. And Sakshi, can you, I guess, mention a little bit about NZTC, but also the ALTA program, I think, is about to commence, which a lot of the audience may not have heard of before. So it'd be great to hear a few words on the scope that's being developed there.
Yeah, of course. If I can just I've got a couple of slides, if I can get them up. So very quick intro on NZTC for those who might not be aware. So Net Zero Technology Centre, we were established in 2017 and we're part of the Aberdeen City Region deal. So we have, I guess, our aim to fund technology development within the Northeast sector, but also looking wider into the UK, Scotland and into the UK as well. We are an industry-led technology research and development organization. So essentially we fund technology projects, like I mentioned before, through to high TRLs, just before commercialization. And we're very much here to support companies and organizations in the energy industry towards the net zero goals that we have. So we've got 3 key areas: Offshore Energy 4.0, which is the team that I'm in. We've also got emissions reductions and energy system integration. So if I get onto the next slide, I can speak about ALTER very briefly. So ALTER, Offshore Low Touch Energy Robotics Autonomous Systems. As you can see, we're doing this in collaboration with the ORE and Orca Hub, alongside other industry partners as well. So essentially the aim of ALTER is to provide a RAS service to the UK offshore sector. We're looking at so ALTER will be looking at the really high TRL levels. So that little gap, that I say little, it's maybe more than just a little gap, but the gap between high TRL and actually getting the industry to adopt the technology. So looking at long-term field trials, looking at certification, validation, reliability, repeatability as well. And essentially a place or a space for academia, industry, supply chain, everyone to come together and connect in deploying a RAS for the UK sector. The outputs of ALTER will be a knowledge portal, a data hub, so shared analytics platforms, and also the competency hub as well. So we're also targeting training and upskilling and reskilling of people, as well as the test and certification side of robotics as well. So that's a super quick intro, but if there are any detailed questions, I'm sure we can take them in the panel later on, or I can try and answer them in the Q&A as well.
No, thank you, Sakshi. And I think as well, if there are some more detailed questions, Andy Bell, who heads up the ALTA program for NZTC, we can take those questions away and get back through email afterwards. But that was a fascinating look at the ALTA program, and I, for one, am really excited to see how that develops over the coming years. So thank you very much, Sakshi. And I think that discussion really sets the scene nicely for the Q&A at the end of the event. So please do post any questions that you've come up with as Ivan, Sakshi, and I have been speaking, and please rejoin us later on where we'll answer them along with our 8 technology developers. So I'll keep the introduction to this next section nice and brief, as we've got a lot of content to get through. So ourselves, Orca Hub, and the Net Zero Technology Centre have nominated 6 technology developers from our programs to present today. It's a really diverse and exciting mix of technologies we've got coming up over the next hour. So let's get started without any further ado. Remember to post your questions. We'll try and answer as many of them as possible, and we will follow up by email on any that we don't get to in the discussion today. So our first guest is Dr. Puyan Khalili, who is co-founder and director of Robotics. So welcome, Dr. Khalili, over to you.
Yes, hello. Thank you very much, and thank you for organizing this event. So yeah, I'll walk you through Robotics, what we do, the problems that are facing the industry at the moment, and the product offerings that we have in order to tackle some of these issues, essentially. So let me go to the next slide. So Robotics' vision is to essentially revolutionize the inspection and asset management industry by providing novel NDT technologies that can be seamlessly integrated onto all types of robots. Essentially the current market position and also the issues that are facing the industry, I'll walk you through those. So the NDT inspection market is set to grow to 13 billion by 2024, and a huge chunk of that, around 30% of it, is ultrasonic testing techniques. But when we look at traditional testing in these sort of scenarios, only 5 to 10% of the costs are associated with the instruments and the technologies themselves. You know, on the right-hand side, you can see that you know, the major costs are associated with access costs or labor costs. It could be rope access or scaffolding in this case. So it is clear that robotics can help and make a difference. We've already seen that the visual inspection market has already taken off, and the global inspection robot market is set to grow by around 4 billion by 2024. And the next logical step is essentially the contact-based NDT inspections. So to walk you through the current technologies that are out there. On the one hand side, we have the contact-based piezoelectric technologies, where a piezoelectric element is used to generate the ultrasound, and using a couplant, it could be water or gel, to transmit that ultrasound to a structure to obtain inspection data. So on the positive side, they have good sensitivity and are quite compact and light, but because you would require a coupling medium, it means that you would require surface preparation, and they also have quite poor high temperature performance, which doesn't make them ideal for robotics implementation. On the other side of the equation, we have, if I can get that's the one, if I can get that. So yes, so the other side of the equation, we have the non-contact EMAT technology, essentially, where the ultrasound is actually generated on the surface itself without any coupling, using electromagnetic mechanism, essentially. So this means that you wouldn't require any surface preparation, and also the ultrasound can be generated and received over paint layers or coating layers. And also, because they are non-contact, you have very high temperature performance. Conventionally, however, based on, you know, you can see one of the examples on the left-hand side, the electronics are quite large and heavy, 3 to 4 kilos usually, and they are very quite high power. They run at thousands of volts peak to peak, which makes them not ideal for robotic implementation in the field. So if I can go to the next slide, please. Yes. Our current technology that is commercially available is Sonus, which is the smallest and the lightest EMAT acquisition system that is on the market. It is ultralight, and it's designed to be used on all types of robots. So it weighs under 290 grams. And it is fully wireless, so it transmits all the data wirelessly to a base station or a robot. And because it's quite important to have essentially the robotics community to have that ultrasonic data or the inspection data readily available to be integrated on all sorts of ways. The system has robotic operating system on board installed, which allows it to seamlessly talk to all robotic platforms that are working with the system. It has powerful signal processing and acquisition systems on board. So everything, all the data processing and the signal acquisition is done on board, and the end result is essentially wirelessly outputted to the robot. It is very low power, therefore it can be quite light and small, and it is also battery powered, which makes it ideal for implementation on platforms where essentially the payload is quite critical, such as the drones. So the capabilities of the system are non-contact thickness measurement, which is essentially used for corrosion mapping. The system has 2 independent channels, which can be used for defect detection or crack detection. And we're also working on adding different capabilities to the system, which would allow it to do rapid structure screening from single points, essentially, without the need to scan the entire structure. So if I can go to the next slide, please. So to go along with that acquisition system, we have essentially the sensor heads. So different types of EMAS are used for different types of inspection, essentially, for different needs. So just to show you the system on essentially being implemented. So if I can go to the next slide, please. So I have a video here, if I can play that. Right. I'm not sure how I'm doing with time. Please let me know.
Just give us one concluding thought, and then we'll have to move on to the next, next presentation, please.
Yes, so if you could go to the last 2 slides, I think I will be able to finish it off. Right. So yeah, just to sum up, I think we are short on time. Robotics is a new startup. We came out of the NDT group at Imperial College with help from Orca Hub. We developed new technologies for robotic inspections, and we are essentially trying to become the NDT data provider for existing and upcoming digital twin technologies. The product offerings that I showed you today are commercially available, and so yeah, we'd be interested to hear from you for your applications. So please feel free to get in touch. Thank you.
Oh, thank you very much, Puyan. Apologies for rushing you at the end there. We're on a really tight agenda, so plenty to get through. But please stay on, and we'll return to Robotics in the Q&A at later on in the afternoon.
Sure. Thank you.
So next up, we've got Dr. Jonathan Schwab-Vilners. Hopefully I've pronounced that correctly. Apologies if not. To present on a new technology which is emerging from some research being done at Heriot-Watt University. So welcome to the stage, and you've got kind of 8 minutes to present your slides. Thank you very much.
Thank you, Alex. Yeah, hi everyone. Yeah, I'm a research fellow at Orca Hub and Heriot-Watt University, and I'll talk a bit about first how we are involved with Orca Hub and how our work fits in this, and then about the research we're doing in autonomous inspection of offshore assets. And we're doing this based on a custom software and hardware solution we have developed. And we call this an autonomous underwater inspection payload. And we use this to autonomously and online collect data, as well as how we use this data to generate some type of reports that are a bit more readable for humans. And I show some field trials and results from examples from this. And then we are currently on the way to commercialize quite a lot of this, as well as some additional things that I will not have time to show. So if you're industry or in research collaborations, you're very free to contact me afterwards. Next, please. So the first line, if you go to Orca's webpage, is saying the Orca Hub is a multi-million-pound program aimed at addressing the offshore energy industry's vision for a completely autonomous offshore energy field. And this is pretty much exactly what we are trying to do. So we are looking at how to combine autonomy, path planning and control with mapping, surveying, and inspection to pretty much release a robot close to an offshore asset. And then the robot will do the complete inspection and return telling us it's done so we can retrieve it. And this has multiple benefits. It can improve the efficiency of the inspection while reducing the human risks as we move them to onshore instead of offshore, which also can reduce the cost and the carbon footprint. Next, please. So in this image, you can see we have a Falcon equipped with our autonomous underwater inspection payload, which is the yellow housing sitting below it. So this housing contains a stereo camera setup, and so a DVL, a fiber optic gyro, and IMU, and some pressure sensor, and in this case also a sonar. We can also attach any type of additional sensors to this, and we've also been using it with manipulators. It also contains additional computational and graphical processing units, so we can run all of our system online on board. Thank you. So one of our main software components is our simultaneous localization and mapping system. So this is tracking how the features in the environment to create a map while it's localizing itself. And it's doing this with enhanced images as well as dehaze. And this can increase our viewing range from what in the North Sea is probably a few meters on a good day to usually at least twice where the distance where we can still reliably track features. In addition to just tracking features, we integrate all the internal navigational systems, sensors, and as well as doing an autonomous online collaboration between all of these different motion estimators. So we don't need to have a precise model of how everything is connected to each other in the beginning, but it will figure this out over time. We're also working on how to include acoustics from sonars into this mapping system. So, and in the image, you can see on the left, like how our system compares to a ground truth, which was captured by a motion capture system. And as you can see, it's very on par. It's pretty much the same compared to if you would use just the inertial navigation system. Next, please. So, and on the autonomous side, we have pretty much 4 different levels of how autonomous the system is, and it's all quite a gray level between these. So it's not either or, it's like mixed and match based on what the robot is doing. So the first level is manual, where it's pretty much how vehicles are controlled today with a joystick, and our system is just overlaying the data so you can see how the map is, where the robot is in this environment, etc. Next is the supervised. So interrupting these joystick commands, we can instead make sure that the robot is safe. We make sure that it doesn't collide with any of the mapped objects, and it can do waypoints navigation instead. Next is shared autonomy, where the robot's actually suggesting what to do, and the operator has to work together with the robot. And this is a way for us to build trust into the system between the operator and what we have been developing. for them to later take the step to full autonomy, where it's you start the mission and then you retrieve it when it's finished. Next, please. I think you skipped one. Yeah, thank you. So one thing we've done is to improve the SLAM based on having it working together with the autonomy. So if we lose feature tracking during operation, it is autonomously able to go back to a point where it thinks it has a good chance of relocalizing itself within a previous map. And this has multiple benefits. It's the main point is to keep a single map of the environment, which means a better accuracy, which in its turn means improved safety because you know where more precise where objects are, so you won't collide with them. And it's also beneficial for performing reconstruction in the end. Next, please. Another example of what we're aiming to do in the end is showed here, where we do an autonomous inspection of an offshore wind turbine. So in this example, the robot has no idea about what is around it. It just knows it needs to inspect something. So it is started close to an object, and then it will start to try to find out what should I do next to get new information about this object. And now you can see it jumped forward a bit in the movie, and it has started to map a part of this structure. And it will continue doing so until it thinks it's done with the current task. So here we didn't do the whole thing because we had some issues with the very strong currents at the operation. It will soon move forward a bit where we see a larger piece of the structure has actually been mapped. So, and we can actually here you can see the different suggestions the robot has made. So while it's in full autonomy mode here, you can also, an operator could select one of these displayed poses, and if it thinks this is a better option to go to, and the robot will go there. So we can go to next, please. And from the same inspection, this model was generated. So yeah, after the mission, what you're interested is the data, and here is a 3D up to scale representation of this with color corrected. And you could actually then in the model zoom in, look at the very detailed parts of this, or measure the size of things by clicking and dragging or just clicking. And we want to do multiple tests at the same point over time to be able to make some analysis about how is the biofueling changing. Is there more corrosion somewhere? Has there new damages come, or has any of them grown so they need repair? And how is the surroundings? Is their score protection still good in the bottom and so? And I think this would be very important to do, as we've seen last week on the east side of the UK, where we had massive storms damaging lots of, changing the land a lot. So, yeah, and thank you very much for this.
No, thank you very much. That was fantastic timekeeping. So that was brilliant and a really interesting presentation as well. Fascinating to see how this kind of subsea inspection technology is progressing. So next up, we have Lee Wilson, who is co-founder and CEO of Honeyworks, to tell us about what they're doing also in the subsea robotics and autonomy space. So Lee, welcome to the stage, and you've got 8 minutes. Away you go.
Thank you, Alex. I'll try and do as good a job on the timekeeping as well. So yeah, we're a subsea robotics startup based in Aberdeen. And we've also got team members in the US and the New York area. And we've got extensive experience in the field of autonomy underwater and on the surface, subsea intervention, manipulator control, remote operations, all of these good things. And we're developing next generation deployment model and operations models for subsea vehicles. I'm going to share a little bit about what we're doing as a company, but I'm also going to talk a little bit about the history of subsea robotics and some of the more general challenges of developing these next-gen technologies and deploying them, because we've learned a few things the hard way over the years. And then related to this event, I'll just touch on the value of the ecosystem that we've been talking about so far in the chat. So yeah, I mean, subsea robotics are not, it's not a new technology to our industry. We've been using them for over 40 years. I've been working in this industry for 20 years and seen some amazing developments in that time. In the preceding 20 years, the real pioneers, and I was lucky to work with some of them, they really enabled a step change in how subsea operations were performed. With this, the humble ROV, and we called them vehicles, but make no mistake, although they were human controlled, these were robots. They were a tool designed to support human efforts in these dangerous or inaccessible environments. So the humble ROV went from a diver assistance tool in the early 80s to, in the 90s, being an enabling technology for deep water developments globally. And that's important to note. They were an enabling technology, and that's what really propelled them forward at scale and at pace. And a lot of this happened on our doorstep here in the UK. So we've got a lot of heritage to be proud of here, and we should continue to develop that. So yeah, on the next slide, the technology has continued to develop, super fast. We've got vehicles that can go into even deeper waters. They can go further offshore. They can have more payload, more power, more tooling, more sensors. We've seen a move towards autonomy. Vehicles that can think and move for themselves, ROVs that can be piloted from shore, tasks that can be automated. We did some incredible work when we were at Subsea 7 developing the AIV. We did that with a company called Seabite, who were a spin out from Heriot Watt. So it's great to see groups like Orca Hub still continuing to push the needle today. But despite all this fantastic, advances in the vehicle tech itself, I would argue that we haven't seen an uptake at scale of some of these new robotics technologies. And even the existing tech, the existing vehicles are, only modestly utilized. And we asked the question, why is that? So we're going to look at the next slide. And, possibly you might argue it's despite all those advances in the vehicle tech, the fundamental deployment or operating models has never changed. You get a big boat and you lots of people on board and you splash the robot into the water, charge a day rate for all the kit and people on board, and typically mobilize for every eventuality you can think of, because it's expensive to get these systems out into the field. But that said, there's a reason we have this model. It's difficult to deploy these vehicles through the splash zone. That's a huge technical challenge in itself. We've got very remote work sites. They're miles offshore. And we've got human operators and sort of life support systems for these robots. It's an incredibly complex field. And but we've got a challenge on our hands if we want to scale some of these new subsea technologies further, in terms of cost and carbon footprint. The huge vessels potentially no longer sustainable for some of those emerging blue economy sectors. And that's one of the arguments I would make, is that it doesn't matter how good the vehicle technology is itself, if it can't disrupt the model or the economics of these operations, or uniquely enable something we couldn't do before, like the ROV did, it remains an incremental improvement, and it's difficult to then commercialize that at scale. So Honeyworks was founded to change the model, not just develop the next increment. So if we can have the next slide. We're proposing a completely different approach to deploy subsea vehicles, because sometimes that incremental change is not enough. We have to create an incentive to switch away from the established way of doing things. So our approach is to remove any form of surface vessel for the deployment of subsea robots. The overarching philosophy is a submersible mothership, this loggerhead concept that's pictured here. And that's developed purely to deploy other subsea robots to the work site. It's a power and communications gateway between the subsea vehicle and onshore operators. It can be built and operated for a fraction of the cost of conventional surface vessels and with zero emissions. So we go to the next slide. There's a few things that underpin all of that. The submersible mothership itself, but the other pillars that we're developing are this notion of onshore control networks. That's something we've been commercializing this year to support remote inspection in the North Sea. To connect the humans in the loop to the offshore work site and to this new deployment model. And thirdly, a high level of shared autonomy, of local collaboration between the mothership and the deployed vehicles, so we can maximising the endurance and reliability of these offshore missions. Because even although the humans in the loop, they are remote, and the machines might need to determine appropriate courses of action for themselves. So that's our mission. We're motivated to make subsea robotics more accessible for a range of market sectors. We go to the next slide. And that's important because, you know, we need to work subsea. You know, if we have there's a huge, you know, amount of growth forecast for the wider blue economy, and whenever you need to work at sea, you invariably need to work subsea, and you need robots to do it. So all of that talks to even greater opportunities in the future. It's an exciting time to be in this sector, and you know, bridging the sectors as we were discussing in this forum today is really important, because this is not easy. Go to the next slide. You know, with subsea robotics, the normal innovation challenges apply. You know, there are things, the unknown unknowns, the things that trip you up. You may end up with an upside down robot here, but subsea, you've got added spice. You know, it's more expensive typically to do anything underwater. LiDAR doesn't work, GPS doesn't work. The material and complexity drives costs up. It's difficult to test it. You know, how do you advance your TRL levels? How do you access a representative environment? You could get a test tank, but how do you get into salt water or pressure or waves or currents? It's a conservative space. You know, there's a lot of incumbent players, established ways of doing it. How do you build that network and encourage people to take the journey with you? And if you're a new entry, that's even harder to the market. And it will be even harder and take longer than you think. So you definitely need to get all the support you can. And that's one of the great things about this workshop and these forums. It's an opportunity to share knowledge. If we skip to the final slide, you know, we've talked to a number of bodies over our journey so far at SolidWorks. Sometimes feels like there's too many people to talk to, but the support is there. There's so much expertise in this area, people that will give you their time. You know, some of these have supported us with use cases, you know, networking, etc. And some of those 30-minute phone calls have been almost as valuable as the grants that we've received. Well, almost. So if I could sign off with one thought, really, it would be to encourage everyone that's either developing or looking to use these technologies to engage the ecosystem. You know, we need that network effect. We need to share use cases, develop pilot opportunities, secure funding, and we'll capitalize on that opportunity to create the next UK subsea robotics success story. So yeah, thanks for listening to my rapid fire rant, and yeah, hopefully it was interesting.
No, thanks, Lee. That was absolutely perfect, and lovely to see that, I guess, reflection on where the industry's come from as well, in the context of kind of where it's moving along to as we move forwards. So we're going to move from the sometimes very deep below the water to the very high above the water now, and over to Chris Chislak, who's the founder and CEO of Bladebug. So I'm very much looking forward to seeing what Bladebug has been up to over the last few months. Over to you.
Great, thank you, Alex. Yeah, so hello everyone. My name is Chris Chislak. As Alex said, I'm the founder and the CEO of Bladebug Limited. It's a pleasure to be here today and present to you all Bladebug, the future of wind turbine repair. What I'd like to do is just give a bit of a background, I set the scene a little bit about why we're doing what we're doing. So we've developed Bladebug, which is a 6-legged walking robot, and it enables wind farm owners, operators to increase the productivity and the profitability of their wind farms by reducing the cost and the risk associated with offshore turbine repair. And just to put this in numbers, onshore and offshore, there's about 1 million wind turbine blades currently spinning around the world. And these all need to be inspected, they all need to be repaired to make sure that these turbines are operating as efficiently as possible and, you know, generate as much cheap electricity and green electricity as they can. If we go to the next slide, please. If I focus on offshore, offshore wind has really significant sustained growth forecast for the next sort of 30 years, increasing from about 40 gigawatts of installed capacity today to over 1,000 gigawatts by 2050. Now, along with this increased growth of installed capacity, the turbines themselves in offshore turbines in particular, they're growing too. Vestas has recently announced their Vestas 236 turbine, a 15 megawatt giant. Once installed, it will be 280 meters high, and each blade being in excess of 115 meters in length. And offshore, it's much less mature in terms of how onshore turbines are maintained, and but it is a rapidly maturing sector. And as technology advances, we've seen how that has affected the price. So the cost of the levelized energy of offshore wind has halved over the last decade, and it will continue to fall with advances in things that help reduce the cost, such as advances in operations and maintenance. And the reason this is important is, if you go to the next slide, please. The current solution of maintaining these wind turbine blades offshore is fundamentally rope access technicians, and this is kind of, it's not fit for purpose anymore. It's becoming outdated. And what we see is it's expensive. It's extremely dangerous. You know, owners, operators, regulators, insurers, they don't want to be sending people out to these assets, especially as these new wind farms are going to be hundreds of kilometers offshore. There's a huge skill shortage, and you know, these costs, as these turbines continue to get bigger and further from shore, continue to increase as well. Now, there are some examples of where technology has sort of been helping along the way. So drones, for example, are really excellent at performing visual inspections of rotors and identifying potential defect areas, but they cannot repair. And working platforms, they're great for removing some of the risks for technicians, but you know, these are, you know, they're bulky, expensive logistics, and they're not fit for a majority of activities. If we go to the next slide, please. And then to make things worse, offshore wind turbines themselves add major challenges for maintenance, and particularly for robotics. You know, these are isolated individual assets. They've got numerous areas that require inspection and repair. They have complex geometries. They have different materials, you know, composite materials, metallic structures. They have awkward and confined spaces, and there's also large numbers of repetitive tasks, such as bolt inspection. So if we go to the next slide, please. So this is what we have done. We've developed Bladebug. Now, this is the answer to be able to perform repairs and detailed contact inspections safely using a robotic solution. It's a six-legged walking robot. It adheres directly onto the surface of the wind turbine blade, and it enables these detailed contact inspections and repairs to be carried out remotely. This stuff, you know, you can do things quicker, you can reduce the shutdown time of the turbine, and overall, you know, improve the efficiency and the profitability of these turbines. Now, the robot's capable of working alongside technicians in a cobot sort of configuration, but it's also more than happy to operate as a standalone and remote device. Next slide, please. So what is Bladebug? Well, broke it down, it comprises of two fundamental elements. The first is a patented robotic platform. Now, this is a six-legged walking device. It adheres directly onto the surface using vacuum cups. We have these highly articulated legs that can adapt and conform to the changing geometries that you see on a wind turbine blade. And this means actually it's not limited to just the blades. There's other areas of the turbine that the robot is more than capable of operating on. And secondly, what we have within this robot is a modular tool payload. So we are essentially agnostic to what the robot is able to achieve, be it inspection or be it repair. And this approach of being tool agnostic, it's great for trying to future-proof the design, because as new tools and new sensors, you know, some of which we've seen during this talk, they can be very easily retrofitted to the robot, and suddenly the robot is capable of performing different activities without any changes to the robotic platform itself. Next slide, please. So one of the unique sort of USPs of Bladebug is this ability to conform and adapt to different geometries whilst maintaining like a constant sort of walking gait and locomotion. And now this agility and this flexibility, as I mentioned, this enables the robot to walk on a blade, inside the blade, at critical areas such as the leading edge, but also inside the tower, for example. So we're currently working on a project with GE Renewables where we're using the robot to walk around the circumference of the towers at the bolted flanges, and use existing ultrasonic inspection techniques to measure the tension within the bolts. If we go to the next slide, please. As an overview of the robot, it's a teleoperated device, so we are remotely controlled. So you have a very simple system to maneuver the robot. So the robot, whilst being complex and you know, very clever, to actually operate it is a very low skilled task. We have a tether, so the robot has you know, power data, but also a safety line connection. We've got these multiple degree of freedom legs that enable it to do this adaptation to different surfaces. And because we've designed it for the offshore environment, we've specifically made it small, compact, and lightweight to remove any concerns about logistics. If we go to the next slide, please. So the robot has been designed with that end user in mind as well, so enabling that precision control, but with a low technical skill level to control and operate. And this versatility means that more tasks can be performed, including using tools for, you know, working alongside technicians, so we can do some cleaning and sanding, highly repetitive tasks, but we can also do highly skilled tasks such as repairing cracks and filling areas on the blades by upskilling staff who are not rope access trained but are suddenly able to now perform activities on blades. And you know, this will lead to further innovations, you know, to improve turbines efficiency, you know, applying new coatings, working without human intervention for this sort of ecosystem of autonomy. If we go to the next slide, please. And this future vision of this autonomous ecosystem, it's kind of seen by the industry. So the graphic on screen now is borrowed from the Offshore Wind Innovation Hub, and it shows that ecosystem with autonomous vessels, autonomous drones. Very helpfully, they show Bladebug being the device that performs the contact inspections and repairs on the blades. But this is how we see the robot working, and we're building up to that sort of element now. If we could go to the next slide, please. So just to bring you up to sort of the present and where we are now, we performed our first offshore wind turbine blade walk in November 2020 on the Offshore Renewable Energy Catapult 7 megawatt turbine in Scotland. And this was a build-up of, oh, running over time, I'm really sorry. I will try and wrap up. So this is a build-up of 3 years of hard work with the catapult, testing on all their facilities from a single cup to the full-scale robot that we have now. And we're currently performing pilot trials over the next coming year to get it out into commercial activity. So I apologize for running over, but that is me in a nutshell, or Bladebug, I should say. No, sorry, Alex, I had to rush the last bit. I got lost of time.
Not at all, Chris, not at all. Thank you for a really interesting look at Bladebug, and for those who haven't seen it before, it's a really exciting technology coming through. But we'll come back to you in the Q&A as well to explore in some more detail. But for the time being, let's move on to a totally different topic, and that's looking at kind of wireless communication. So welcome, Felix, co-founder and Chief Technology Officer of Hydromea. So please, over to you, and you've got 8 minutes or so to present on Hydromea.
Yeah, thanks very much for inviting me. Great honor to be on the panel. So we are Hydromea. We are a Swiss company specializing in remote robotics, autonomous robotics, and underwater communication. So you can go, please, to the next slide. Yeah, thanks. So my co-founder, Alexander Barr, and myself, we've spent over a decade in academic research trying to build basically miniature autonomous vehicles that can be operated in large swarms where the robots cooperate with each other and then perform missions like environmental monitoring and pollution mapping. And you can see the Vertex AUV that we developed mostly within academia still. And starting this journey many years ago in 2003 in Australia, in the Australian National University, and then later at MIT in Boston and EPFL in Switzerland, we realized very quickly that what holds this technology back is the lack of being able to communicate and being able to position or localize where the robot is, because GPS doesn't work underwater, radio doesn't work underwater, there's no 5G. So that makes it really difficult. And while we've seen our drone revolution in the aerial space, I think this is still a big challenge in the underwater domain, especially when it comes to smaller vehicles. Because as long as you have a tether on the back, you have to drag this around and you can never really freely move and be autonomous. So you're always dependent on some support ship. So that's what we've concentrated on in our research, is to solve the communication problem and the localization problem. And then we founded Hydromea exactly 7 years ago to bring this into the market. So if you go to the next slide, please. Yes, and then last year we joined TechX, and we had a great time talking to a lot of people in the industry in Aberdeen and trying to find the best places where we can apply our expertise in robotics and communication. And we now, this year, we are focusing on remote inspections with a wireless drone, which we developed. To the next slide, please. Yeah, so the problem that we identified, which we heard over and over again, is that inspections offshore are inefficient. You need, as Lee already mentioned, you need these big ships. They're very expensive to run, very expensive to mobilize. It takes a long time to get out there. And this clearly has to change to make this sector sustainable and make it more cost efficient. So we see a trend towards resident autonomous vehicles, and especially for us, we see a lot of opportunities for very small scale vehicles, because most of the time having a look is all you need to do initially, and then you want to make the decision if you actually have to mobilize bigger equipment to do repair work. But for a lot of jobs you don't need that, you just need a visual inspection tool or some sensors on location. So that's what we're working on now. Please, next slide. Thank you. So this is X-Ray, that is our current wireless drone, the first wireless miniature drone underwater based on optical communication to do live video streaming within like a 50-meter radius around an access point. And that really frees us up to inspect very complex infrastructure with a lot of pipes and valves and things in the way where a tether would easily get snagged. So currently we're focusing on confined inspections, the confined spaces like ballast water tanks, or also within hydropower turbines, or other places where it's very tight and where a tethered vehicle would easily run into trouble. And then we will move further into open water operations later. So I think on the next slide, we have our roadmap. Yes. So as I said, so this at the moment, this year and next year, we're focusing on the confined inspections. And this is a remote controlled vehicle, but remote controlled via the wireless optical link. So that already makes life a lot easier, because you don't need extra people to manage the tether. You don't have to be concerned about getting tangled or hooking up, or if you're in a ballast water tank, having to undo the cross stitch that you've done with a tether flying through this space. And then the next phase, starting next year, will be to go into open water. So we're targeting offshore and aquaculture markets, and we will enable the vehicle to navigate in larger volumes autonomously until it reaches the access point, the wireless access point, where you then get the wireless video transferred. So then a human pilot can interact with the robot to guide the inspection. And then once inspection is done, the robot can autonomously navigate back to a dock or to a recovery point, which is also in line with what other companies are doing, like Oceaneering, just on a much bigger scale. So our specialty is to make things on a very small and cost-efficient scale. And to get a camera or a sensor onto a location, you don't need a big vehicle necessarily. There's a lot of things you can do with very low-cost small vehicles. Phase 3 will then be to go into autonomous operations. I think we've seen in the talks before that this is where the trend goes also of Orca Hub, is that we see the remote control as a stepping stone, and then that will merge into sort of assisted pilot control, where the vehicle is semi-autonomous and does a lot of tasks automatically, but the pilot can still guide and interact with the robot. And then the last phase will be full autonomy, where basically you drop the robot off and you pick it up a few hours later with all the data that it collected, and then you can just send that back to the to shore via a satellite link or some other fiber uplink. And lastly, the last phase, within 5 years, we aim to have a multi-robot system with swarming and autonomous operation, autonomous deployment, autonomous recovery. So this will look into docking stations to recharge and offload the data and deploy the vehicles when they're needed. So our vision really is to have these vehicles installed on the assets. And that's why we're aiming at having low-cost vehicles to basically enable that every asset could have a robot that you can just send out if there's a problem and have a look at things and inspect regularly. Yeah, and so this is our technology roadmap. Next slide, please. So we have a few enabling technologies that we developed over the years. So the first one is maybe a little bit mundane, but very important. So we developed a very compact underwater thruster, which we also offer as a product. And it has no central hub, which makes it very robust against tangling. So I have one here, if you can see the video. So it's rim driven, and any debris gets just sucked through the center. So that makes the robot much more robust against fouling or fishing lines and water plants and so on. Next slide, please. Yeah, I think we can skip to the next one. Then the next technology that I've already mentioned is that we've pioneered wireless optical communication, because we saw this as a major stumbling block, that if you don't have wireless communication, you're always limited by a cable. So our current product, Luma X, offers 10 megabits per second over up to 50 meters through water. So you get enough speed to transfer HD video in real time with very low latency. And we're currently working with industry partners to push this into the offshore environment to install these at crucial sites. And we've seen a lot of uptake already just to connect to underwater sensors. So on the next slide, you can see an example. Yeah, so this is, for example, a small ROV reading out an underwater sensor wirelessly. So you can essentially have data loggers that record data, and then you can go there and retrieve the data without having to plug in a cable or without having to retrieve the instrument. And we have similar applications on a much bigger scale in the North Sea with work-class ROVs wirelessly connecting to gyro boxes and other sensors that are used during installation of offshore equipment to get a live feedback of the orientation of the manifolds you're installing. So this has been very, very helpful to give real-time data to the operators to see what's going on without having to worry about cables or other inefficient methods. Yeah, next slide, please. Yeah, and lastly, we also have a lot of research background to do swarm localization. So that's basically what our PhDs have been about in our academic days. And we still have this DNA in the company to build up this technology and build up all the puzzle pieces we need to have truly enabled underwater scalable robotics, where you have basically the same situation as in air, that you have localization, you have communication between robots and also from robots to the operators and to the shore, and enable subsea autonomy. So especially a key factor with the underwater optical communication is also we're very active in the standardization of this. We're part of the SWIC group that defines the standard for underwater optical comms, so that other robots can then also tap into this infrastructure. Yeah, so lastly, so that's the final goal in 5 years, is to have these swarms of, so you can stay at this slide. Yeah, it's okay. You can to have these autonomous vehicles that can cooperate with each other, collect data simultaneously on large volumes, and really bring the scale that instead of doing things one by one with big ships and manually with humans in the loop, that we can move to a situation where you have large numbers of robots that can work simultaneously at a relatively low cost compared to the big ships, and also eliminating all the oil having to be burned and the carbon footprint of these large vessels and the large costs that they incur.
Can I ask you just to conclude your thoughts, please, Felix?
Yeah, sure. So now with X-ray, because it's a visual inspection robot, we've now also moved into computer vision and machine learning and AI to do visual inspection tasks and visual navigation. And that, of course, ties into the localization solution that we've built up already. So I think we have like a very good handle on number of key technologies that will help us to push this to fruition. Thanks very much. And also, last thought, so we are welcoming partners and pilot customers next year, because we are looking actively for opportunities to trial this in different industries. So if people have ideas where any of this can be useful, please contact us.
Oh, thank you very much, Felix. That was a fascinating look at hydromia. So it's really interesting. And on to our final presentation of the day, last but certainly not least, we'd like to welcome Kieran Hope, who is the Chief Operating Officer of Air Control Lentech. And we're going to hear about the company's visual inspection technologies. So Kieran, I'll hand over to you for our final presentation of the day. You've got 8 minutes.
Thanks, Alex. I think it'd be good just to recap actually over, from being last, I've actually been able to have a good listen to what everybody else is saying as well. And I guess, from where we've come from, we started as a drone company back in 2015, 2016. And we very, very quickly realized, once we were starting to operate in the North Sea, that, being just a drone company and focusing on one issue was never going to be quite sustainable for us. And we needed to break out into different robotics. So now we actually do ROVs, we do robotic crawlers, and we also do drones. A lot of the technologies I've seen being spoken about. Now, if I take blade bug, for instance, it's very, very focused on blades only. But what about, because if the guy said, oh, drones, it's not great for blades because they can't repair. But what about the nacelles? What about all these other types of technology? So if we look at the whole, from a wind turbine from under the water all the way through, yes, some of these technologies are great, but they're not great just to be able to do one thing. We are going to need a multitude of different technologies to overcome some of these challenges. And that comes back to probably around to where I now see, we are very, very well placed to make comments on this purely because we do a lot of class approval work, which, for instance, floating wind now comes under class approvals. So when we say full autonomy, in majority already, the technology's there, from what I can see, and from individual technology developers. One of the biggest problems I think is going to be is regulation in terms of what class will accept as inspection data. Whenever we're on FPSOs, for instance, doing class inspection, the class surveyor wants to be there, even though we're accredited to do these types of inspections. They still want people there because they've effectively got to sign off on the asset. So another challenge I really see is contractual issues. It's going to in turn have decreased deployment in technology. We've seen this in oil and gas for years. It's never changed. And I think from that side of things, people in training as well is a huge issue. I'll give you an example. We are currently trying to promote, trying to employ 15 drone pilots alone. And we've had 30 applications, not one of them had a drone pilot license. So, there needs to be a huge focus on people in training. Not so much the technology. I think the technology is actually readily there. But, there's some refinements need to be done. So I'll just give you a brief overview on one of the projects we're working on. So this is a phase 1. I can't talk about phase 2, unfortunately, because it's undergoing patents, etc. So we were approached by an oil and gas operator in must have been about 2019, 2018, and they had a challenge of inside modules where there was maybe fugitive gas emissions, and they weren't able to reach them. The only way that they were able to do that is by rope access. So I'll go to the next slide, please. Sorry. So what we've decided to do, and working in conjunction with the Net Zero Technology Centre and the oil and gas operator, is to develop a lightweight multi-rotor UAV, which has got internal flight capability and can work in confined space environments. This is quite challenging for drones. There is only a couple in the market there that can do this quite successfully. And also have external flight capability as well, because we don't want to just be able to do one thing. We see technology. If you take so many different technologies now and look at what they can and can't do, the reason a lot of these are probably not getting utilized is the cost. So if you look at going into development of something like this, you're talking £2-3 million. If you have one of these on each asset, it's going to be extremely hard to make money on that. So we need to try and make these things do as many different tasks as possible. So we can also have the ability to pinpoint where gas leaks are occurring visually. So we know out there in the market there is, there's tools out there which have been used in the North Sea, and there's a big splash in the press at the moment. But they're all gas sensing, so they sniff for gas. As you can imagine, North Sea can be quite windy, so not the best tool for the job, but certainly the technology is moving in the direction of visual detection of these types of hydrocarbons. Now, this technology will be cross transferable, as we already are using in different environments. So offshore oil and gas is a huge market. There will also be, the maritime sector, where you've got large vessels, like bulk carriers, even polyurethane plants. There's so many different refinery plants, and when we move to blue and green energy, this is going to be quite a vital tool as well. Next slide, please. So the project status at the moment, as you can see from some of the photos, the guys have been on live site trials. We have, obviously due to COVID, it's been pretty difficult to get onto some of these sites. So we've done onshore testing so far, but we are due to go out in the field offshore early next year again, once we get, maybe hopefully try and get back to a bit of normality. So the latest revision of this phase 1 of the craft's in the final stages of development, and personnel are currently being trained in operation of the craft, which is almost complete. And we're also looking to secure further site trials. So if there is anyone on the call today that would like to get more information on this, then just give me a shout. I know there's some guys here today that we already work with. So yeah, just give us a shout if you do need some access to this technology. Next slide, please. As I said, multi-industry use. It was initially designed and manufactured to tackle an oil and gas industry problem. However, through our research and development process, we found that the product could actually be deployed across a variety of industries, as I did mention. So, as we go through this process and we speak to, we've got hundreds of customers now globally, and we're constantly discovering new use cases for this technology. So it's certainly been a good one to run with. But our goal is to provide a commercial UAV with the ability to address problems in complex and operating environments. Now, autonomously, probably not. I think for us, the technology to do autonomy is there, but it's not really what the market wants. And I don't think we need to be shoehorning ourselves down a route where we're going to spend a lot of money and it's not actually going to be utilized. I've seen that in the oil and gas industry so much before. But for us to go fully autonomous is not going to take too much of a turnaround. We're probably talking about a year's development. So next slide, please. Yep, so that's the end of my presentation. If anyone's got any questions, you can feel free to contact me in the email or speak to me in the Q&A. Thank you very much, Alex.
No, thank you very much, Kieran. And that's been a really exciting tour of 6 fascinating developments in this robotics and autonomous system space. So thank you to all our panelists. And it's now time to dig a little bit further into what we've heard today and take some questions for the panel. So please do put them in the Q&A if you've got any burning questions for anybody who's presented today. And panelists, thank you for holding on while everybody's been presenting. So please do put your cameras on so we can all see who you are, and let's kind of get started with some questions. So I'd like to start with you, Puyan, if I can, with your first presenter. And how do you balance the sometimes competing challenges of kind of weight and power in designing your inspection system? Does that sometimes present some conundrums?
Yes. So obviously, with any technologies, you have trade-offs that are essentially you need to manage in order to have the optimal solution for the application that you're looking at. So majority of these systems that are out there in the field are essentially majorly designed for manual inspection and these sort of scenarios. So when we look at robotic implementations, you need to look at it as a completely new way of thinking about it, and different scenarios that come into play, and different challenges that are there to be faced. So there are trade-offs to be had. So we looked at we looked at the hello.
Hi.
Can you hear me?
Yes. Yeah. You went on mute for a couple of seconds there. Are you still there?
I think it's probably the Wi-Fi. So yeah. So for developing the technology that we have done, we looked at the challenges and also the opportunities that were out there. And we found that by developing a system that has that is achieved lower power output and achieving the same sort of results, we were able to develop a essentially come up with a solution where
I think that's your Wi-Fi potentially playing up again, Puyan. So I might move on to another question. We can come back to you if your connection improves. So if I can come to you, Ivan, and I guess to ask a question, kind of more high-level question. What do you see as the main benefits of not starting from scratch with these technologies? So clearly there are similar use cases for a lot of the either technology components or entire systems across different sectors. What do we gain by harnessing these synergies between different sectors? You're on mute.
Yeah. Apology. I think what you do is you give the end users the chance to de-risk their technology and better, because a lot of the use case for robotics are actually the same across lots of what I would call extreme environments, and that goes from nuclear, offshore, but construction is also for me an extreme environment, and all of them need roughly the same thing, but they're not coordinated. So they're all saying, oh, it's too expensive to develop. But if you could tell them, look, if you pull together your resources, we can develop technology that can have an impact across a large number of sectors. Even if you look at subsea, you've got aquaculture, you've got offshore oil and gas, you've got renewable, you've got mining, you've got... So you really have to look at this and see how you can get them to pitch in to de-risk the technology, I think. And that can be onshore and offshore as well.
No, that's really useful. Sakshi, do you have anything to add to that?
Yeah, I was just going to add, so at NZTC, we did extensive work with our roadmaps. I dropped a link into the chat for everyone earlier. So we actually coordinated some extensive workshops to collect everyone's thoughts around the use cases for different technologies and the technology gaps, which I think was a really, really good exercise. And I think on the back of that, there's maybe an action to take for half these industries that we can collaborate with to link in with, Orca Hub, with Orca Hub or with ORE or with NZTC, so that we are sharing practices or sharing developments and sharing the cross use cases within different industries as well.
No, that's brilliant. Kieran, you've put your hand up. Have you got something to chip in with on this talking point?
Yeah, I hear Ivan saying, it's working with end users, but I see there's a massive gap here where, yes, end users employ the technology, but there really needs to be engagement with accreditation societies. So for instance, your ABSs, your DNVs, your Lloyd's registers, these guys are the ones that are actually going to accredit the technology to be utilized in the first place. It's not really up to end users as to what is going to be allowed to be used. We've come across this in oil and gas, and I think there needs to be a bit more knowledge shared between people and understanding what the actual protocol is to have these inspections classified. Because if you just go to an end user and end user takes something on, the class society might say, no, sorry, we're not going to use that, and you're going down a whole rabbit hole, wasting a whole heap of money. So I think it's certainly somewhere I would start now, before you go any further.
Yes, this talking point seems to be generating plenty of interest. So I'll come back to Sakshi and then Ivan in that order, if that's okay.
Yes, so I was just going to add very briefly is that is a really good point. There is a gap there to fill with certification and accreditation, but I think there's there's a challenge here where we can create opportunity within, where we can shape what the accreditation or the certification can be like. So there is a bit of back and forth between us and those certification bodies. So it's not for them to tell us prescriptively what to do, but we can also tell them, because they're also sitting in an unknown space in terms of robotics and AI and how we certify them for use. So it's certainly a challenge to overcome, but we have to do it together. It's not one telling the other, in my view.
And Ivan, did you have something to chip in there as well?
I wanted to add, I think that the ecosystem is really important. I think it's something we have quite unique here. If you look at today's seminar, you've got SMEs, you've got academics, you've got already catapults and Net Zero Technology Center, all there trying to pull in the same direction. I think that's quite unique. It's very rare, I think, across Europe to see that happening. And we have a unique expertise in the offshore renewable sector, certainly, that we should capitalize on. I think, to me, the key to success is to have a roadmap that enables us to do easily technology insertion. So it's clear that we're not going to go from fully autonomous, I mean, what we have now, which is big ship with big crew, to fully autonomous in a day. We need to have a roadmap where we can encourage academics, SMEs, and large operators to work together and to insert the technology at the right time, so that we keep the confidence of the end users. I think if we can do that right, I think then I guess the future is ours.
Felix, I'll come to you as well.
Yeah, and overall, our experience was that the class societies are very interested in these new technologies. Of course, they also have to make sure it satisfies their needs. And normally the standard is if it can do an equivalent job as a human inspection in the past, and maybe they will have to adapt certain things. I think the crucial thing is that there's a gap, because first, as a technology developer, we have to be able to demonstrate our system in a relevant pilot, which means we already have to invest all the work and money to bring the technology to almost commercial state, basically. Because the robotics, you cannot really do pilots, especially underwater robotics, you cannot do pilots with a hacked together prototype that you've built on a weekend. It has to be done properly, and it takes time and resources. And I think that's where these funding programs from NZTC and similar programs, and also the access to the industry and access to pilot facilities and trials, is really, really helpful to bridge that valley of death, basically.
Yeah, that's a really interesting point, and I'll maybe open up to Lee and Jonathan. Do you have anything to add on kind of the testing of subsea technologies and some of the hurdles that represents?
Yeah, it's incredibly difficult because you've got a big gap between your validation environments and the real one. We put a lot of effort into simulation, and that was great for verifying behaviors and logic and decision making. And you could emulate the physics and the environment to a surprising level as well. But there's always that gap between the real world and sim. And closing that needs to be done in a controlled manner, but needs to be done in a collaborative manner. We had some great success with operators in the North Sea because everyone was on the same page. Everyone was subscribed to the potential benefit. And if the prize is big enough, then people will work together to make that happen.
Jonathan, anything to add before I go on to our last question that we'll have time for?
No, I agree very much. Like, yeah, going from simulation, we develop all of our as well, and to actually showcasing, it's still like a lot of work of engineering to take it, and because it's too much uncertainties going on with offshore trials.
I have to say, I think that's where maybe AI is going to help us in the future, because there's some emerging models where you can actually learn quite quickly from in simulation and then adapt that learning to the real domain reasonably quickly online. So I can see at some point we're going to be able to get 90% there in simulation, 95%, and then do the adaptation to the real situation quite quickly. But not in the next 2 years. I mean, it's going to take a bit more time to get there.
And so we've just got time for one more question before wrapping up. And there were a couple of kind of linked questions for Chris in the chat and the Q&A there. So Chris, with Bladebug, have you tried testing? I think you might have answered this in the chat already, but if not, have you tried Bladebug on any kind of imperfect blade surfaces? And another question from the chat was whether kind of what plans you have for a first maintenance activity after doing the first blade walk that you talked about.
Yes, we have walked on rough blade surfaces. So again, I kind of overran time, but so we've been working with the Offshore Renewable Energy Catapult since 2017, developing each stage of the robot on real turbine assets, and that includes a very fondly titled blade graveyard, where they have a number of old scrap blades that have been left in the car park to weather. They're heavily fouled. They've been tested, they have cracks in, and we've been testing and validating our robot on those primarily. And that's essentially the worst case scenario that you'd get for blades. So we're very happy with our sort of vacuum cups performance, our vacuum system performance on those surfaces. So that's one thing. In terms of what we can do, we performed lightning protection system checks on the lever mouth turbine. We've then validated that with a rope access technician alongside to quantify or validate the results. We're currently working on 2 projects. One is leading edge repair, so that's using the robot to sand, clean and reinstate material to the leading edges of wind turbine blades, which is a very key area. It affects all wind turbine blades, it reduces performance. The second project is, I mentioned, we're working with GE Renewables to use the robot to inspect the bolt tension inside the bolt tower. So I don't know if Kieran missed it, but I was saying the robot that we've developed is much more capable than just a blade inspection and repair device. We actually can operate all over the turbine, actually on many other different assets as well. So it is a very versatile system, and they're the areas that we're working on at the moment. So inspection and repair, with repair being longer lead time just because that's more bespoke as opposed to the inspection where we're using existing equipment that we can essentially just bolt onto the robot and just use it remotely.
Yeah, Chris, sorry, I wasn't trying to single you out or anything. I'm more
no,
it's
fine.
I'm more meaning from from our experience in doing these inspections. We've operated for 5-6 years now in oil and gas, and one tool doesn't do everything. So we need to, one of my follow-ups from here will be to contact some of the guys out of these presentations and say, look, what can we actually do together here? Because there's so many different ways to, and one of the issues I always see is cost. Cost is a huge thing. Now, if you ask me, are we going to get completely manless inspections of wind turbines, for instance, offshore? I'm going to say no. I physically don't think it's possible, even with the greatest technology there, because I understand the challenges that are there, and I just don't think they can be overcome. And if they are to be overcome, they're going to be too expensive. If we're looking at the margins that are there at the moment, you're talking 5% margin on a lot of offshore wind projects, whereas you're maybe looking at 30 to 40% in oil and gas. So people are still not focusing time and energy on what needs to be done in offshore wind. But I think there's a way that if people are working together, for instance, us, yourselves, and some other companies, there may be a way to be able to package up something which can then, if you've got multi-skilled technicians, we can drive the cost down again. There's different ways to skin a cat, but I wasn't meaning to single out. It was more just, I think there's a lot of different technologies would be required to be able to complete that, and not one sort of tool fits all. So
yeah, not so. I was joking.
I mean, I think that's a really nice, Kieran, that you've kind of flagged that you see opportunities to work with some of the other presenters on today's webinar, and if that's an outcome from today, I think it's been a really successful afternoon.
Yeah, I mean, Alex, absolutely. I mean, this is what things are all about. We've been part of the NZTC. I think we were the first company ever funded by NZTC back in 2017, and we've worked with a number of different technology companies that have come through the NZTC. Even the one that we're working in at the moment. And we've got 2 other technology companies assisting us with this project that we met through the NZTC. So these are what all these events are all about. They're all about sharing knowledge, sharing technologies, and then looking at how we can deploy them at the most cost effective to the operators, and how can we get as Sakshi said there, the class approval stuff. We've got experience of everything's driven from IAC, so with the class approval guys, they'll just say, well, you need to do what a human can do, and that's it. Be all and end all. So that that's sort of stuff we come up against. But if we've got a bigger army going back to them and saying, well, actually, we can do X, Y, and Z, and this is how we can do it. It's not all a cost bearing on one company. If you can spread that cost across 5 or 6, and we just need to try and I think the technology is majority already there in terms of being able to do robotic inspections in person, which is what class need at the moment. The cost base is too high for operators to use, so we now need to see if there's a way we can all work together and try and see if we can reduce costs to be able to for the guys to use it. So
yeah, no, thanks for that kind of concluding thought, Kieran. And I guess all it remains to say really is to thank all of our presenters today, from ourselves at RE Catapult, as well as NZTC and the Orca Hub, as well as the 6 technology developers. So thank you very much indeed. The video of the webinar is going to be posted on our YouTube channel tomorrow morning. So please, if you found something of interest, go back, rewatch, pass it on to all of your colleagues, your friends and family, maybe an early Christmas present. We will email out the recording and links to reports mentioned today, as well as any additional answers to Q&A questions that we didn't get around to this afternoon, sorry. And you'll find RE Catapult, Net Zero Technology Centre and Orca Hub on LinkedIn and Twitter. So please do follow all 3 organisations for much more exciting developments in the RAS, AI, digital innovation space, as well as upcoming developments in the Alta project, which was mentioned close to the start of the webinar. So thanks again for joining us. Enjoy the rest of your days, and we'll see you at the next one.
Cool. Thank you. Bye-bye.
Thank you.